Good morning students. In this video we are going to see Unit 1 Laws of Motion, learning objectives, understand about impulse and impulsive force, know about Newton's third law of motion, understand the derivation of principle of conservation of linear momentum, and also know about rocket propulsion. First let us see about impulsive force. What is called impulsive force? A large force acting for a very short interval of time is called as impulsive force. A large force acting for a very short interval of time is called as impulsive force. If the force is larger and the time interval is very small, it is called as impulsive force. See this diagram. Here a ball hit the stem and it takes place within a minute. So, it is a very short interval of time, but the force is larger. What is called impulse? When a force F acts on a body for a period of time t, then the product of force and time is known as impulse, and this impulse is represented by J. So, what is called impulse? The product of force and time is called as impulse. The product of force and time is called as impulse. When a force F acts on a body for a period of time, then the product of force and time is known as impulse. So, the force acts on a body within a time at a particular time is called as a impulse. It is represented by the letter J. The formula to find out impulse is F into T. Now, let us see the derivation for impulse. So, by Newton's second law, F is equal to delta P by T. Here delta refers to change, and what is P? It is linear momentum. So, F is equal to change in linear momentum by time. Now, from this we have to find out delta P. So, delta P is equal to F into T. Now, what is F into T? It is impulse. You know that the product of force and time is impulse. So, which letter we have to use for impulse? J. So, J is equal to delta P. So, F is equal to delta P by T. It is according to Newton's second law. That is, according to Newton's second law, force is directly proportional to rate of change of linear momentum. So, F is equal to delta P by T. Now, from this we have to find out delta P. So, delta P is equal to F into T. Now, what is F into T? It is impulse. So, J is equal to delta P. Now, from this we have to see that impulse is also equal to the magnitude of change in momentum. That is, impulse is equal to change in momentum. Now, what is the unit for impulse? The unit for force is Newton, and then the unit for time is second. So, the unit for impulse is Newton second. Otherwise, the unit for force is kilogram ms minus 2, and then for time it is second. Now, s minus 2 and s, we have to subtract this, we get s minus 1. So, the unit for impulse is kilogram ms minus 1 or Newton second. Change in momentum can be achieved in two ways. So, change in momentum can be achieved in two methods. The one is a large force acting for a short period of time. Large force acting for a short period of time. Force is larger, time interval is very small. And then second condition, a smaller force acting for a longer period of time. The force is very small, but the time interval is very long. So, based on these two conditions, the change in momentum takes place. Now, examples for change in momentum. Automobiles are fitted with springs and shock absorbers to reduce jerks while moving on uneven roads. So, while moving on uneven roads in automobiles, they have to fit with springs and shock absorbers. So, what is the reason? To reduce the jerks. And in cricket, a fielder pulls back his hands while catching the ball. So, while we watch the cricket, a fielder pulls his hand back to catch the ball. So, he experiences a smaller force for a longer interval of time to catch the ball. He experiences a smaller force for a longer interval of time to catch the ball, resulting in a lesser impulse on his hands. So, if the force is very small, the interval is long, then only the impulse will produce very less. So, according to the condition of impulse, change in momentum, if the force is very small, the time interval is long. If the force is very large, the time interval is very small. So, according to this condition, a smaller force produces a longer interval of time, then only the lesser impulse will take place in hands. Newton's third law of motion. Newton's third law states that for every action there is an equal and opposite reaction. They always act on two different bodies. See this diagram. Here for every action there is an equal and opposite reaction. Here see the first bob, it produces a force, and then see the last bob, it also produces a force. So, for every action there is an equal and opposite reaction. This action and reaction always act on two different bodies. Here the first and last bob produces an action and reaction. So, it will take place in two different bodies. So, if a body A applies a force Fa on body B. So, here first bob is a body A and last bob is body B. So, here the A produces a force Fa on body B, then the B reacts with the force Fb on body A. So, if A produces a force Fa on which body? B, then the body B also produces the force on body A. So, which is equal to Fa in magnitude, that is the body B also produces the force equal in magnitude of the body A. That is, if the Fa produces 5 Newton force, means Fb also produces 5 Newton force, but opposite in direction. The first bob produces force in one direction, means the second bob produces force in opposite direction. For example, if A produces right to left, means then B produces left to right. So, we have to use the sign minus. Now, examples for Newton's third law of motion. When birds fly, they push the air downwards with their wings. See this diagram, the birds push the air downwards with the help of their wings, and the air pushes the bird upwards. What happens here? The air pushes the bird upwards. So, here the air downwards with their wings is an action, and the air pushes the bird upward is the reaction. And when a person swims, he pushes the water using the hands backward. See this diagram, he pushed the water by using his hand. So, it is the action, and here the water pushes the swimmer in the forward direction, it is the reaction. When you fire a bullet, the gun recoils backward. See here, to fire a bullet, the gun recoils backward and the bullet is moving forward. So, and the gun equalizes this forward action by moving backward. Here the bullet is moving forward is the action, and then recoiling of the gun is the reaction. Now, let us see the topic, principle of conservation of linear momentum. There is no change in the linear momentum of a system of bodies as long as no net external force acts on them. So, let us prove this statement by using the derivation. Now, see this diagram, m1, m2, body A having a mass m1 and body B having a mass m2. It moves with an initial velocity u1 and it moves with an initial velocity u2. Let two bodies A and B having masses m1 and m2. So, here two bodies having masses m1 and m2 with the initial velocity u1 and u2, and all these bodies are moving in a straight line. Now, let the velocity of the first body be higher than that of the second body. So, here u1 is greater than u2, that is the velocity of A is greater than the velocity of B. Now, during an interval of time t second, they tend to have a collision. So, within a time t second, both the bodies A and B collide with each other. See this diagram, they collide with each other. Now, after the impact, both of them move along the same straight line. After they collide, they have to move in a same straight line. See this diagram, here both the bodies are moving in a same straight line. Now, here the velocity changes as v1 and v2. That is the body A having velocity v1 and body B having velocity v2. So, here the force on body B due to A. Fa is equal to m2 v2 minus u2 by t. The force on body B due to A, that is the body A produces a force on body B. So, the force is Fa. So, here what is the mass of the second body? m2 and velocity v2 minus u2 by t. Force on body A due to B. Now, what is the force on body A due to B? Fb is equal to m1 v1 minus u1 by t. Now, by Newton's third law of motion, action force is equal to reaction force. Now, here we have to use Newton's second law, F is equal to mv minus u by t. Okay. Now, here we have to use the Newton's third law, action force is equal to reaction force, that is Fb is equal to minus Fa. Now, what is Fb? m1 v1 minus u1 by t is equal to minus m2 v2 minus u2 by t. Now, in this derivation t and t get cancelled. So, m1 v1 minus u1 is equal to m2 minus m2 v2 minus u2. Now, you have to multiply this m1 v1 minus m1 u1 is equal to minus m2 v2 and minus becomes plus. Now, we have to bring final velocity to one side and initial velocity to another side. So, m1 v1 plus m2 v2 is equal to m1 u1 plus m2 u2. So, the above equation confirms in the absence of an external force, both the objects A and B move without any external force. So, the algebraic sum of the moment after collision is numerically equal to the algebraic sum of the momentum before collision. So, after collision is equal to before collision. When the after collision is equal to before collision means in the absence of an external force. It is very important in conservation of linear momentum. If there is no any external force applied on a body, the algebraic sum of the momentum after collision is equal to before collision. Hence, the law of conservation of linear momentum is proved. Now, next topic, rocket propulsion. Propulsion of rocket is based on the law of conservation of linear momentum as well as Newton's third law of motion. So, rocket propulsion based on law of conservation of linear momentum and Newton's third law of motion. Rockets are filled with a fuel, either liquid or solid. It is filled with a fuel. The fuel may be either liquid or solid in a propellant tank. When the rocket is fired, the fuel is burnt and a hot gas is ejected. See this diagram. When the rocket is fired, this fuel is burnt and produces a hot gas with a high speed from the nozzle of the rocket, and it produces a huge momentum. To balance this momentum, an equal and opposite reaction force is produced in the combustion chamber. So, to produce this momentum, the equal and opposite reaction force takes place in the combustion chamber, which makes the rocket project forward. So, hot gas is ejected. To balance this, an equal and opposite reaction force is produced in the combustion chamber and it makes the rocket to move forward. So, while in motion, the mass of the rocket gradually decreases until the fuel is completely burnt. When the fuel is completely burnt, what happens to the mass of the rocket? The mass of the rocket gradually decreases. So, there is no net external force acting on it. The linear momentum of the system is conserved. So, here no any external force act on the rocket. So, what happens to the linear momentum? It is conserved. So, the mass of the rocket decreases with altitude. When the height increases, the mass of the rocket decreases, which results in the gradual increase in velocity of the rocket. So, what happens to the velocity means the velocity increases. So, the mass of the rocket decreases with the height. Then what happens to the velocity? The velocity increases. So, at one particular stage, it reaches a velocity which is sufficient to just escape from the gravitational pull of the earth. At one particular stage, it reaches a velocity. That velocity is just escape from the gravitational force of the earth. Now, this velocity is called escape velocity. So, the mass of the rocket decreases. What happens to the velocity? Increases. So, at one particular stage, that is it reaches one particular velocity. At that velocity it escapes from the gravitational force of the earth. This velocity is called escape velocity. So, what is called escape velocity? At one stage it reaches a velocity which is sufficient to just escape from the gravitational pull of the earth. This velocity is called escape velocity. Thank you, students.